Hello guys, how are you? I welcome you to my channel, which is Introduction to Aerospace Engineering, and we have actually covered some of the videos related to engineering, aerospace concepts, flight dynamic concepts, numericals, theoretical portions. So you can visit the other videos and you can go through and you can have an idea what sort of the concepts that we are actually just producing through our paperwork and notes, and you can go through and have an idea. And if you are interested, you can also visit our another channel, which is Nota Bene Tech on Tube, and you can have the concept of another business oriented videos as well. So right now what we are doing is some of the recap that we're going to actually provide you that we have covered in the last some of the videos, so that we can provide you the approach towards the concept of propeller, which would be the main focus of our video. What led us to provide you the concept of propeller? That was because of the some of the last videos, starting from the thrust efficiency trade-off, and you can get an idea what was the reason that we reached to the concept of propeller, especially to be discussed in this video. And as you know that thrust and efficiency, just giving you a recap in terms of the notes, we discussed the thrust and efficiency trade-off, we discussed about the mechanism, and also there was 4 mechanism, which was the reciprocating engine propeller combination. There was a turbojet, turbofan, turboprop, and we discussed about efficiency and thrust and relationship of all these two, especially in the 4 mechanisms, and what is the best possible mechanism for a given aircraft. And low speed aircraft, we normally actually see that reciprocating engine propeller combination is well suited, and rest obviously is for the higher speed aircrafts. But for the low speed aircraft, number 1 actually a mechanism would be discussed, and we have discussed in detail relative to that mechanism. What we have discussed, we discussed about the concept of the useful power available divided by total power generated, which was PA is less than P, which was the external, and obviously normally power is generated, and in case of the reciprocating engine and power combination, you mean that there is internal power generated by the engine because of the shaft or crankshaft, that is P, and the external power is generated by the propeller, that is PA. PA is always less than P. And we also discussed about the device, a propeller device to be placed in a laboratory, and we derive an equation in terms of kinetic energy, in terms of velocity, and in terms of power. And also we discuss how we're going to have that actually power, especially PA, which is this T into velocity, V is to velocity, that is the combination, and we discuss about how we reach that form of the equation, and because of the propeller device to be placed at different positions in the laboratory. And we discuss in detail, and also we what we reached was the efficiency in terms of the reciprocating engine propeller is very high as compared to the thrust, which is very low. And also because of that, we discuss the mechanism, we discuss about the efficiency and thrust trade-off, and afterwards we discuss about the 4-stroke engine, which is related to that. The introduction of the videos, and afterwards we 4-stroke engine, we discuss in detail the 4-stroke engine, we discuss about the specific fuel consumption, the equation of that, and also which was normally the weight of fuel consumed for a given time increment divided by power output into time increment. So that is how we also discuss the units of this specific fuel consumption, which were normally is not as commonly used as in these standard international units. So what we discuss in detail, specific fuel because of that four-stroke engine, we reach the specific fuel consumption. When we're talking about the airplanes, we know that there is a velocity, the airstream velocity, and also we know that there is an altitude h because of the of an airplane. So when we discuss about velocity and altitude in terms of specific fuel consumption and in terms of power, which we have obviously generated from our this power and also the specific fuel consumption, which are the formula which is actually told. So obviously how these two will affect variation or velocity and altitude, or velocity and altitude will be affected by will affect these power and specific fuel consumption. So that was the next video that we discussed in detail, and also we derive the relationship that P is reasonably constant with velocity, okay, and P, which is power, is proportional to air density rho, which is obviously directly related to the pressure. When the pressure changes, it's obviously related with height. Okay, so when specific fuel consumption is constant with velocity, and specific fuel consumption is constant with velocity with altitude h and h as well. So this was the crux of that video, that variations of these two can be actually related to the variations of the other. And afterwards, we discuss about what we discuss about. The variation of this, and then we're going to discuss about the concept of a propeller. The propeller is normally at the outside of an airplane, and we're going to discuss how it will relate to all the four concepts previously discussed. So I'm just going to actually give you what an idea, so that we can obviously reach towards a conclusion that how we're going to actually discuss the propeller. That would be the last video of the reciprocating engine propeller combination. We have discussed about the engine, we discussed about the different variations of different components, and also now we're going to discuss about the propeller, the structure, and how we're going to actually use it in terms of velocity, in terms of angle of attack, in terms of you can say the relative wind direction. We're going to discuss about the relative distance as well. We discuss about the alpha, we're going to discuss about the beta, we're going to discuss about this whole relationship in terms of velocity and in terms of relative distance. So that of an airplane, that would be our core goal. We're going to discuss about the propeller in terms of the different scenarios. When we talk about the fixed one, we talk about the two-way, and also we discuss about the constant. So these are three of the ways, and also we're going to discuss some of the equations as well. And when we going to discuss about the propeller as an producer of velocity and a producer of thrust, and when we're going to actually discuss the tip of the propeller also working as part of the propeller and eventually producing some results. So how these are interrelated, we're going to discuss this right now. First of all, I'm going to read out the notes which are in front of you. The procedure is Wilbur Wright 1902 was the first to actually discover, or actually sorry, the invent the propeller. Propeller is a twisted wing oriented vertically to the longitudinal axis of the airplane, and the forward thrust generated by the propeller, that is normally at the outside, and obviously the forward thrust is generated by the propeller, and is essentially analogous to the already or the aerodynamic lift generated on a wing. So that is the what, the thrust, okay, the forward thrust, that is directly proportional to the what, aerodynamic lift, that is the aerodynamic lift generated on a wing, that is the aerodynamic lift generated by the wing, and that is the forward thrust, that is the two proportional. So obviously the forward thrust will be produced by the propeller, and that will eventually create a lift because of the wind, or on the wing, sorry. And power available is always less than P. I have discussed it already. Net power through engine propeller combination is always less than the shaft power transmitted to the propeller through engine shaft. Propeller efficiency is defined as this, which is this and this. This is the propeller efficiency, which is less than this. Propeller efficiency is a function of advance ratio J, and J is equal to what? A stream velocity or free stream velocity divided by n into d, where n is number of revolutions per second, and also that is the propeller diameter. Okay, so that is how you're going to actually relate the propeller efficiency to the velocity and n and d. So this is first of all the definition, and the inventor we discussed about the efficiency, the propeller efficiency in terms of J, and obviously we're going to now discuss you can say a pictorial relationship. First, in case of A, we have this is known as the propeller. Okay, normally it is in this form, so we are just discussing this propeller and discussing the information over here. This is the chord line, and this is the relative wind. Okay, this is alpha and this is beta. When you talk about alpha and relative to the because of the relative wind, that is alpha. When we have beta relative to chord line, we have this. Okay, so this is how you're going to have beta and alpha, which is what the relative wind, and also we have what chord line, we have the angle of attack. We give it because of that it is a lift angle is generated. Okay, and lift angle first, sorry, actually there is there is the lift is actually generated. Okay, and also it will give us the positive impact, and the velocity is decreasing. This is RW, which is the relative distance. Okay, this is the pitch angle beta, and this is alpha is the angle of attack, and this is the A stream velocity. Now we see that the angle of attack is the angle between chord line and the local relative wind. Absolutely right. This is the angle of attack definition. Pitch angle beta is the angle between airfoil chord line, this one, and plane of rotation. Okay, the angle, this is the plane of rotation, and this is the chord line, so that would be the beta angle between the two. And alpha depends on what? This alpha, which is the angle of attack, will depend upon the velocity, A stream velocity, and R into W, which is the relative, which is what? Is the relative distance. So when velocity would be very, very low, okay, alpha would be obviously very, very high. Okay, just to reciprocate and manage. And also when we discuss about that, when that would be high, that will give the lift L in direction of the thrust. So velocity has greatly increased, all parameters remain same. That would because has greatly increased, all parameters have remained same. That is in figure B. So there in figure B, this has increased dramatically, not dramatically, but we have, just for the sake of the comparison, in this there is a decrease in the velocity, there is an increase in velocity, all keeping all parameters the same. Obviously we have a larger alpha angle or angle of attack, okay, because of the increase of the velocity. Okay, so but the lift would be produced in the opposite direction, obviously, and that would be negative as compared to the A. So here the relative wind has moved to the other side of airfoil section, giving rise to a negative alpha. Okay, here the relative wind has moved to the other side of airfoil section, giving rise to a negative alpha and an aerodynamic lift force L pointing in the opposite direction of positive thrust. So some conclusion would be the local angle of attack, and hence the thrust generated by the propeller depends critically on V of this and Rw. Note that Rw evaluated at the propeller tip is d by 2 into 2 pi n, or which is Rw tip into pi n of d. That is how you're going to show it when you're going to have it the evaluation at the tip of the propeller, that is normally by the tip of the propeller. You also give some of the effect as well. So this relationship is because of that tip, rw tip, and ratio velocity r divided by r, which sets the direction of the local relative wind, is this. Okay, this one is this. Obviously that sets the direction of the relative local relative wind, and v over this divided tip is equal to, get this relationship, and velocity over pi, and d is equal to j over pi. So advance ratio J, are dimensionless quantity, plays a strong role in propeller performance. Obviously when we're talking about the J, we say that it plays a very important part in the propeller performance. It is an advance ratio, and we have discussed the advance ratio in terms of velocity, A steam velocity, and d, which is the number of revolutions per second by the propeller, and that is d is the diameter. Obviously that is understandable. So but we have to add on the tip as well, so that will give us the wholesome effect. So J is similar to M, and RE, which is Mach number, and Rayleigh number. So that is also similar to this. That is obviously, you can say, a dimensionless quantity, but obviously it is a quantity, and it is similar to the Mach number and Rayleigh number. So that means when we talk about J, we're going to talk about the you can say propeller. That it is understood. When we talk about the Mach number, we normally say that is the plane speed, or relative to the wind. So that is we're going to discuss the Mach and the Rayleigh. That is a separate. We have discussed earlier, just given the idea and some of the numericals, I believe. But this is the part we're going to end at this time. But I'm going to discuss in detail. So that means the revolutions per minute by the engine, when it will going to decrease, it will decrease at the fixed throttle setting. Okay, so height would increase and lift would also increase, and P is directly proportional to RPM. P is directly proportional to RPM. That means that power, when we're going to increase the power, there will be increase in the revolutions per minute. And revolutions per minute depends on load on the crankshaft. That depends on the load on the crankshaft. Okay, and the aerodynamic torque provided by the propeller, obviously. So RPM depends upon what? Normally the revolutions per minute or per second are normally what are generated by the load on the crankshaft in the engine plus the aerodynamic torque created by the propeller. So that is how the revolutions per minute would be created. That would be directly proportional to the power, directly proportional to the lift. Lift would increase, height would increase, but obviously the RPM of the engine would definitely decrease, and we get the efficiency as well. And we have actually, this is when we talk about the propeller efficiencies, when we talk about this is the maximum at this point, starting from 0, 1, 2, 3, and 4 to 5, giving a declining effect. J is equal to this. So that means the propeller efficiency would normally increase, okay, with the normally this J would normally increase. Okay, that is how it's going to show. And because of that, NPR, which is the relationship we have delivered because of PA is equal to NPR into P. Okay, so that means these two are related. So we have driven a driver, we have actually drawn a graph for this, and this is lift and drag. Lift to drag ratio of a given propeller airfoil cross section. That is lift to drag airfoil cross section. That is how you 1, 2, 3, 4, 5, and this is how you're going to show it. Lift to drag of a given propeller airfoil cross section. 1, 2, 3, 4. These are the two graphs primarily discussed later on, but I have discussed earlier. This is the graph which is for the relationship of altitude and distance. And as a takeoff, that is the distance covered from obviously the distance covered or horizontally, and this is the altitude covered vertically at different position, which is the constant speed propeller. Because of the constant speed propeller, three conditions of the propeller are given. This is now the aircraft, and two position controller propeller. This is the second one, the graph, and that is fixed pitched propeller. That is the third graph. We normally have it. This one. This are three graphs that we have shown. So torque is normally generated. We have discussed about torque over here because of the RPM, load, and torque. Torque is generated by the component of aerodynamic force exerted on the propeller in the plane of rotation. That is, torque is generated by the component of aerodynamic force converted to the propeller in the plane of rotation. Okay, torque is given by the component of aerodynamic force exerted by the propeller in the plane of rotation. That is obviously right. Okay, that is created by the propeller because of its rotation. So variable pitch, that was the second one, that was because of the two position controller propeller, and that was when you can say the variable pitch and the constant speed propeller greatly enhances the rate of climb. Okay, and for airplanes compared to that, you have this one. Yeah, because of this fixed pitch propeller gives you a less altitude as compared to this. With this two position, that is also given as the variable pitch propeller and the constant speed propeller. This is one. These two give a much higher altitude as compared to the fixed pitch propeller. This is been discussed. And we have discussed the propeller. The torque has been provided by the aerodynamic force acting through a moment arm to shaft. So what is aerodynamic component? Give us the what? The rotation of aerodynamic force on the propeller in the plane of rotation, and tending to retard the rotation of the propeller. Okay, this is the RF. That is aerodynamic force, aerodynamic component of the force exerted on the propeller in the plane of rotation. Okay, so later on you can say variable pitch propeller. Because variable pitch, pilot can change the pitch angle, that was what? Beta, and because of the pitch angle is changed, the torque would change, which in turn caused to change what? In the engine RPM away from the optimum value for engine operation. This was partially self-defeating in the quest to obtain maximum efficiency because of power by ranging the propeller pitch. Engine power P was frequently degraded by resulting change in RPM. This constant speed was born. NPRP is optimized, which is equal to this one. Okay, which we normally want to have this power to be optimized, because this is obviously less. This is the power generated by the propeller, and our main focus, because the changing of the pitch or the angle whatsoever, or the altitude, the distance, we normally want to have this power to be optimized. That is why we are doing this one. And the constant speed, normally it has given us the result of constant speed. Why the constant speed propeller was born or came into existence, and normally because of the variable pitch propeller, the pilot changed the propeller, the torque changed, and caused the engine RPM to be optimized or reach to the optimum value, just for the engine operations. And but obviously the concept normally was used in 1930s and 1940s airplanes, but that was partially self-defeating in the quest because to obtain the maximum NPR the varying the propeller pitch, engine power was frequently degraded by resulting change in RPM, and thus constant speed was born. So that is normally, you can actually go through the whole concept again by visiting in the book. And I have just given you concept that what are the three scenarios, how they were actually came into existence, and what are the variable pitch propeller, or the fixed pitch, or the constant pitch. That is the concept, and normally it is related to the altitudes, different altitudes covered by the airplane. So feathering of the propeller, that is also a concept that I'm going to actually show in end of my video. Propeller is a feather when its pitch is adjusted so that the drag is minimized and there is little or no tendency for auto rotation when the engine is turned off, but the airplane is still moving. The propeller is feathered when an engine failure occurs in flight. Yes, and sometimes when a multi-engine airplane is taxiing on the ground with one or more engines turned off, or more engines turned off. So this is the feathering of the propulsion. A propeller is normally feathered when its pitch is adjusted so that the drag is minimized and there is little or no tendency for auto rotation when the engine is turned off. Okay, but the airplane is still moving. The propeller is feathered when an engine failure occurs in flight. Normally it is said that the propeller is feathered when an engine failure occurs in flight, and sometimes when a multi-engine airplane is taking on the ground with one or more engines turned off. So this is the concept, feathering of the propeller, and just to adjust the pitch so that the drag is minimized and there is no tendency for auto rotation. Normally it is, because the engine is auto return, or the engine is turned off, it is tendency for the airplane to actually get an auto rotation. To avoid that tendency and to get the drag, because of, normally that is because of the drag, when the drag would be minimized and that would be adjusted by the pitch, and the pitch would normally be actually adjusted with the help of the propeller. Normally when we're going to feather the propeller. Okay, so this is normally the concept, the whole surrounding the pitch, the drag, the auto rotation, and normally when there is, this normally occurs when there is an engine failure in the flight. When engine fails, normally the pilot comes out because of the parachute. Normally that is the case. Just at that case, when there is engine failure, we are discussing engine propeller reciprocating engine propeller combination, and when we have the airplane flying but engine fails, what would be the function of the propeller and how the propeller will help us to avoid any sort of the damage. That is the part at the end of feathering of the propeller. The propeller will normally act more efficiently. So this is the concept of feathering of the propeller, and I have discussed the propeller in detail, and I hope that I have explained. And if you have any doubts whatsoever, you can just actually let me know in the comment section, and even give it a subscribe, like, or the subscription, or pressing of the bell notification button. I have actually given out the concept from step by step from the previous some of the videos till this video. So we have explained the mechanism, thrust and efficiency trade-off in terms of what? A reciprocating engine propeller combination. So that was the point, and in my opinion that is enough when you are talking about the low speed aircraft. The aircraft normally discuss in a commercial use or for the individual use, this concept is formed the basis for all the other concepts with different variations of equations, with different variations of the components, but more or less the efficiency and thread combination with the relationship with one changing or the other changing or vice versa, the concepts are applicable for the rest of the trees as well. If you are interested, we will able to actually give you one-on-one topic, one-on-one actually give out the information and about the other mechanism as well. You can let us know if you are interested, and we can provide you the separate videos as well. In case if we try to actually discuss some other mechanism, might be in the future, but on the request, we're definitely going to actually provide you the conceptual, which we can actually give take out from the book as well. But just to give an idea, it may help us to cover or actually give take the whole concept in one go in one video. Obviously, that is a more fruitful approach when you go through or actually visit the book or read out the text pages. So that is how I have actually gone through the verbose, or you can say I've gone through the whole concept in terms of the audio, in terms of notes, and I hope that you're going to enjoy our further journey towards understanding the conceptual fundamentals of aerospace engineering and further engineering concepts. I hope that you're going to actually come with us in this journey with sharing and also adding to the subscription list. So till then, for the next video, take care and have a nice day.